According to the planning domain definition language, or PDDL, we need actually to specify two files. The first one was the domain model, which is going to be discussed as part of a file called domain.pddl. And the other is the so-called problem, which is describes the certain things that are associated with a specific instance of the problem we try to solve. So this one is the general description of a domain, and the other is the specific instance of that planning problem we are facing. As we said, we are going to be discussing a domain. Initially, it was presented to be a domain of logistics. For this specific discussion we have here, we need something which is a bit simpler. So we'll be using the so-called blocks word, because it's actually simpler to understand what is happening over there and to have too many object types involved in this kind of plan. So blocks word is going to involve a number of, it's actually one of the classical examples in planning, and it will involve a number of blocks and how we arrange them on a table. Okay, so that was basically the domain. And so as far as the domain now is concerned, we actually have a couple of things that we need to mention here. So the domain is involving the specification of types. These are obviously the usual types we're familiar with, like the equivalent of classes, if you like, in object-oriented design. Let me just write it down. We need to introduce predicates. That effectively state something about the subject of a sentence generically. Okay, so that's something we will introduce a bit more formally in a moment. And then we have the so-called actions schemas, also known as operators. And actually we call them action schemas because they describe actions fairly generically. Okay, that's why we call it schemas. Okay, so the schema consists of the name of the action, so the name of the action and parameters. So action name and with some kind of parameters, also known as variables. And this will actually be the signature that we will see these action schemas being discussed. And of course, it will be introduced a bit more formally in a moment, because we have certain constraints to satisfy about both the action schemas and also the predicates. We also have the concept of a precondition, which is associated with the action schema and describes what are all the prerequisites that we actually need to have in place in order for us to trigger that kind of action, for that action to be able to be triggered. Okay, so and then of course we have the so-called effects, which are, as you can understand, the results of those actions, which is effectively taking the system from one state S to another state S prime. Okay, so this is associated with the state transition that we have seen in other videos in this lecture series. And in terms of specifying a problem, a planning problem in the so-called blocks word domain, here's an example of a problem. We have a table, a surface, and we are going to be specifying here, we just have 3 blocks, A, B, C, as actually shown here. That's going to be, the specification requires, let's say, the initial state, and this will actually be the goal state, C, B, A. Okay, so this will be the goal state. And here is what is a PDDL state consists of. The specific flavor of state in this kind of representation language. So a state, in a PDDL state, is a conjunction of what's called ground atomic fluents. And this basically looks a bit more complicated than it is, but what it ends up being is, let's say, a specific grounded, if you like, a specific grounded, that's where the ground comes from, the grounded, let's say, arrangement of objects that can also involve predicates with parameters or arguments that are constants. So definitely states can change, but as in a specific instance in time, we have, let's say, a specific arrangement of blocks, let's say on the table, okay? And we cannot have variables. We cannot have variables as arguments in a state specification. So for example, this specific state that we have seen, the kind of the state at which we started with, so we have the block, the initial kind of state. So we have the block A, sorry, this was B. This was B. And if I see here, it is A and C. This is basically the other 2 blocks on the table. And so the initial kind of state is described as follows. So we have the predicate on that takes the arguments, the specific object, let's say A, comma, table. So A is on top of the table, and B is also on top of the table, and C is on A. Okay, so this is a grounded atomic, in other words, there is only one predicate involved, conjunction of fluents, and fluents are effectively have the notion of things that actually can change over time as the system kind of operates. Okay, so this is basically the whole specification of a PDDL state. That's what a PDDL state is, which is kind of fairly intuitive. So I don't think you have a kind of problem kind of absorbing it. So let's look now at the action, what we call earlier as action schema. And again, the name is of a schema may be a bit kind of confusing, but think about the schema that you have, let's say, in databases where we have, let's say, type information associated, let's say, with columns, let's say, of a table. And the columns of the table represent, the sort of types that you have, and the specific rows, the specific grounded objects that you have, the specific, if you like, instances of those types. And so similar analogies we actually can draw here about actions. So in the actions, you would expect to see variables. Okay, so an action schema effectively represents a family of ground actions so for example, let me provide an example of an action schema from the block words. So we have an action, let's say, of move, and as arguments, you would expect to see variables. So we have the variable b, and we have another variable x that represents, let's say, a specific location, and another variable y that represents another location. So move a block of something which is of type block p from a location x to location y. Okay, so these, all of them, all three of them are kind of variables. So that is going to be sort of the name, if you like, of the action, parameterized by these specific parameters, which are variables. And the action schema will involve also two other things. The one thing that it needs to involve is so-called precondition. Let me write it like this: a precondition. These are obviously not very formal. The actual language varies, differs quite significantly from what I'm actually writing over here, but this is also the notation that your textbook kind of absorbs and recommends, just to understand what is happening. And then, of course, the syntax is a bit more complicated than that, and it actually takes inspiration from a language that was actually called Lisp. Lisp is still was actually one of the first AI kind of languages, and is still being used to some degree from some kind of legacy applications. But coming back to that, so we have this kind of a precondition. And what is really a precondition? As we discussed earlier, the precondition is the lists all of the conditions that need to be satisfied in order for that action to be able to be triggered. Okay, so let me provide an example of precondition here. In order to move, to be able to execute this kind of action, definitely you have to have this being true. So the block must be on something x, which I actually call x. X could be, let's say, the table. The other condition is that there is b is clear, and clear means here that there's nothing else that it is on top of b, so it actually is clear on that respect. Also, we have to have, in order to move b into another location y, then definitely we're going to have b to be of type block. Maybe this is what we should have written first, now that I'm thinking about it. We also have y to be a block. And another one condition is that the b is not equal to x. Another that b is not equal to y. And another that x and y are different. Okay, so this is a specification of precondition, which kind of makes sense in the case where we can move a block, let's say, from the table to put it, let's say, on top of the C. These preconditions this conjunction needs to be satisfied, needs to evaluate to true. And of course, it will evaluate to true when all of these conditions evaluate to true. So definitely B is a block, so this is evaluates to true. Definitely the Y, so the C is a block as well, so Y is C in this kind of case. B is different than the table. So the X is the table over here. And so let me write this down just to understand. So the B here is the block B, can be assigned the block B. The X would be assigned the table. The Y would be assigned C. And that's basically what the assignments we have done in order to check, let's say, an example of when this precondition is satisfied. Evidently, all these inequalities hold as true, and all of them are true. So B has to be clear in order for it to be able to move in the blocks word domain. We will see some of the rules of the blocks word in the domain.pddl file that we will introduce. Okay, so that's basically an example of a precondition. And the other thing we would like to sort of specify in this action kind of schema is the sort of effect. This is the last thing. So the effect, I'm going to write it down on the last space, the last line over here. So the effect, let me give you an example of an effect. So we have a predicate that, so if let's say the block B is going to be on top of the Y, so definitely the effect should say that, so on B comma Y. Also, since we moved it, and if B was on top of X, let's say on top of the table, then we have a clear X. So this means that since the B was moved, the table now is clear. Okay, so X. And also we have a negative condition over here that this is no longer true. That is fairly intuitive. And I'll try to squeeze another last effect over here, maybe over here, and the clear is not of Y is not true anymore, evidently because now B went on top of it and therefore stopped being the Y to be clear. Okay, so that's basically the sort of effect, and this is the whole specification of an action schema. Fairly generic. It does allow us to very compactly kind of discuss and describe what it is, the precondition and the effects, and therefore determine what will be the state of the system after this action is taken. In another video, we have seen how we can actually launch the repository of the course and the associated, if you like, site in a Docker container. And if you have not seen this kind of video, please review it, as it actually shows you how to effectively get VS Code to be able to launch it in the container. And this is basically what you should be able to see when the VS Code is launched there inside that container. As a reminder, this container, the specification of that container is discussed here in this file, and it is effectively a container which can be launched either in the PyTorch or in TensorFlow. So there are two Docker files, one for PyTorch and the other for TensorFlow. The purpose of this kind of discussion is to allow everyone to be able to see the PDDL in terms of do the syntax highlighting, which is actually needed for us to be able to visualize both the domain and also the problem PDDL files, as well also to connect on a remote solver or planner that the authors of specific extensions have connected to, in order for that problem to be solved and to see actually the actual plan, the actual suggested plan out of that solver. Okay, so in order for us to do so, we need to install an extension which is actually called the PDDL, unsurprisingly. This extension is shown here. And if you type PDDL, when you click on this kind of extensions icon, then you will be prompted to install in the dev container. So we will install it in the dev container, and after a few seconds, then you will be able also to get that extension to install, as it's actually shown here. And this extension is actually a very, very neat extension to support our planning kind of training over here, because it does allow you to connect to, as I said, to a remote planner without really installing anything, which is basically the algorithm that we are going to look at in a bit more detail a bit later, and then solve that planning problem. So the directory lectures blocks world PDDL and the demo.pddl are the corresponding under the planning directory are the corresponding domain file and the corresponding problem file, the problem.pddl file. Okay, so the specific domain, as you click on this PDDL, then you will actually be prompted by you'll be prompted to actually configure some of the things that are needed for this exercise to be completed. So I would suggest that you do install the special kind of icons that are very useful for visualization purposes, and you are also download the tools which are needed for properly parsing PDDL and validating the plans. So you will be prompted with some pop-up windows. I suggest that you click on this override kind of button, and you will be able to then proceed. You need to select the solver.planning domains. That is the solver that we will be using in this exercise. And you will can select either the output window or the search debugger. I selected the output window as the default window that the plan will actually be shown. Okay, that's all with respect to this kind of configuration. And now that we have configured, let's go into the extension. Let's go into understanding a couple and see actually the actual syntax. Earlier, when we were writing things down, we said that we are going to have a simplified kind of syntax, but here is the actual PDDL syntax. So here we are starting with a domain that is actually called blocks world, and we also have the various types. So we define the type of type block, so that's the class. So we have blocks. And we define predicates. We have the on predicate that takes as parameters A and B of type block. We have clear, which we effectively, as we discussed, was when there's nothing on top of that block A. We have the predicate on table, which means that evidently there is a block on top of a table. We have holding. In this specific blocks word, we have also an actor, which is a gripper, that it will actually be the entity that will actually lift the block and move that block from one position to another. And had empty, which effectively indicates the state of the gripper, that it is a very specific state. The gripper is not holding any block. So these are all the predicates that we have defined, and we have a number of actions that follow, action schemas that is. So the action schema pickup, as we discussed, an action schema is defined by the name. The name in many instances have parameters, so the parameters here is actually shown in the second line. So the parameter pickup parameter for pickup is a block and a precondition and an effect. Okay, so we have action for pickup, an action for, let's call, unstack, and is in this case we have effectively two blocks, so we are unstacking when we are picking up from a block from on top of another block, a block from that is on top of that another block, and while the verb pickup, the action pickup, is being used to when we pick up from a table. We have the action put down with its corresponding preconditions and effects. The action stack, which as you can guess, it involves two blocks. Okay, and that's basically our domain. Fairly compact. Obviously, it's a very simple application over here, and that's basically the domain. And so the domain consists of the action schemas, the predicates, and the types that we have. Okay. And the demo.pddl is the grounded specification of what we face right now. So right now we have an initial state. So we have, first of all, the specific objects that that correspond to the types that we have defined. So we have red, green, blue, yellow, brown, pink of type that are of type block, and we have the initial state, and we have the goal state. Okay, so this is our initial state. As we discussed, the initial state consists of we don't see any variables here. We have the specific grounded or objects that we have see grounded fluents, atomic fluents, and that's basically the two states. SI and SG is the term that we'll be using for the initial and the goal state a bit later to discuss. This is what we see here. Okay, so that is basically the two essential kind of files, and how we are actually going to exercise the plan to the solver or the planner. So we're going to effectively right mouse click and select run the planner and display the plan. Okay, so if we actually do that, we don't need to specify any options for the planner. Then we actually see the planner being used, the planning algorithm being exercised, and very, very quickly, as we expect, the problem is very small, the plan to be produced on a separate kind of window. So the plan evidently is optimal in what sense? It sort of satisfies some kind of a cost metric. In this case, it is the minimum number of potentially minimum number of actions that we had to take in order to go from the initial state to the goal state. As you can see here, we have far more number of blocks than we have withdrawn earlier. We have 1, 2, 3, 4, 5, 6 blocks. And so this is the first action, the so-called unstack action, the put down action, and so on, as we can see. And at the end of the day, we have this plan, which involves, I can count right now, but there's a number of potentially finite number of actions until we get into the goal state. Okay, so what will be the goal state? That the red is on top of the brown, the green is on top of the red, and the gripper is holding the yellow. Okay, so that will actually be the goal state, and as we see here, we satisfy the goal state with this with this planner if we do that exercise by hand, which I'm not going to do right now, but please feel free to do that yourselves. Yeah. Also on the output, you can actually see the value of the metric, the number of seconds that it actually took for that plan to be executed, and evidently this plan is the optimal one in terms of number of actions that we have executed here. There are various kind of options for you to export that plan into a .plan file. So if you click on that, then you can get a plan file that you can actually sort of save for that specific exercise. And this plan can actually be read by another software entity, let's say a simulator. As we will see a bit later, we may actually pair this planning capability that tools such as PDDL allows us to develop with a robotic operating system. Perhaps this merging can be done as part of a project, and we have already a project on a warehouse that works like this. And so, saving or passing on these kind of plans, despite the limitations of those plans being deterministic and sort of assuming close words or full knowledge of the environment, nevertheless, they are very good for training and tutorial kind of purposes. So that is the capability that we will be using these plan files for. So the other I think important to recognize is that evidently this is a closed tool. Right now it is accepting PDDL as inputs and spits out this kind of plan file, but it's kind of quite important to be able to have, if you like, a tool that it is in a programming language that we're all familiar with. And closing this kind of discussion about tooling for planning, I think it's worthwhile visiting a library which has lately appeared, trying to unify many of these planners which are around and be able to intelligently select the right planner for the right job. So not all planners are appropriate for all problems that we face. So doing that kind of filtering for us is quite kind of important as well. So that library is called Unified Planning, and it is available inside the Docker container. And here we actually have authored a notebook that allows to solve the blocks word domain in pure Python. Okay, and this is something that perhaps you will feel a bit more comfortable in actually using, and also offers, because it's in Python, offers much tighter integration with the other software entities such as the robotic operating system, so on. Okay, so that is an example of the block words again, and I just want to highlight briefly some of the APIs that are being defined over here. So we have the usual types that we have also met in the blocks word domain. So we have the type of block. So that's the equivalent of how you define the block as a type. We have as fluents in that API, we are absorbing all the predicates under that kind of API. So effectively what we have seen earlier as, let's say, a predicate called clear that takes as an argument an object of type block. This is how you define exactly the same predicate in this tool. The other and so on, you can actually see here the on table predicate, the are empty, holding, and on. All of these are exactly included on as predicates in the PDDL specification. And we also have the specification of action schemas. In the Python API, in this library, we have the concept of instantaneous action. And instantaneous action kind of makes sense because we never talked about duration of actions. These are all enhancements in the PDDL specification that we can actually, that people have actually done. And this is, let's say, the pickup action, which takes as a parameter the object block. And for this specific action schema, obviously we need to start adding preconditions in a similar way as we have seen them, and also define effects. So effects are the conditions that are going to be met when in the new state of the environment. Okay, so these are all the preconditions and the effects for the pickup action, the put down action, the stack, and the unstack actions. Okay, and these are all kind of matching the corresponding actions that we have seen earlier. And obviously we are able to model also the problem using this Python API. So we have here an initial state and a goal state, which is obviously we need to specify in this cell. The objects are the ones that we are actually creating as of type block. They are being created in this kind of list comprehension here, structure, and the we're adding as the objects, very similarly to what we have been adding the objects in this demo.pddl. Okay, so we have here this 1, 2, 3, 4, 5, 6 objects. So what we have as well over here. And then we have the initial values, initial values of all the objects involved and the actors involved. These are all, let's say the arm is empty. And for each of the objects we actually have defined, we are able to assign initial values for those. Okay, so which are on the table. So each one of them is on the table. And we have each one of them is clear. So this is our initial state. And this is obviously this is a bit different than the initial state we have seen over there in this in this PDDL, but it's one and the same thing. Okay, so we have the goal state, which follows. So the goal state is that we have the on top of another object, each one of those objects we have defined in this problem statement. And that's basically it. That is our specification about our problem. And then what we do is we are able to exercise for this specific kind of problem. We are able to select intelligently the planner or the solver that it will actually solve it for us. So this is what's happening in this cell. And with the .solve method is actually being used here to provide the sort of solution, to print the solution for us over here. Okay. Now the solutions are of two types. One is a valid solution, which is actually called here solve satisfying, and the other is the optimal solution, and with guarantees. And in this case, we have a satisfying solution as to how you can actually stack these objects on top of that, on top of each other per the specification of the goal state. Okay, and we're actually able to see some of the graphs that are being considered by the solver, that are being constructed internal to the solver to come up to this solution. We will come back into those graphs when the time comes to look at the algorithms which are powering this kind of planners. And the last graph over here, the last plot, which is supported by the API, is the graphies view of how the plan and each of the sequence of actions that we have to execute in a graphical form.